this time I hope I make it in time. I want to take you a little bit further through the looking glass of Alice and talk a little bit and muse a little bit about how to bring the text beautifully typeset together with the pictures that things like Alice in Wonderland have, and what we have to think about here and what kind of chaos this is introducing. Hans was talking this morning about the chaos, that we know how to do a nice title, but we don't really know how to make a nice book, because there the things get very problematical, and this is really more or less what I'm going to talk about today. So here's a picture from looking glass and a little bit of text, and this is about the theme that I'm going through. Are we in the fast country or are we in the slow country? In other words, are we able to make this problem solvable in a suitable time, and how far and how fast do we need to run to make this happen? And when, which is unfortunately often the case, do we fall down and don't get anywhere? So, yeah, it's going to be a little bit math this time, small doses. If we have pages with text and we have figures where we want to put the pages on, then the general formula for doing that, if we are allowed to put more than one page, one figure on a page, is basically this this little one on top here. If we make it a little bit simpler and just allow one picture on a single page, so that's something like we have 90 pages and we have 30 pictures, and we can put the pictures, 30 pictures on some pages, and then essentially that's the formula. Now, what is this formula, is the meaning of it? Here are some examples. If we do the first 16 pages of that book with 9 figures, we have about, what is this, 11,000 possibilities to place those figures onto the pages if we just allow one figure per page. And if we do a very quick assessment, it would still take longer than the lunch break, namely 3.5 hours, to decide which of those solutions is correct. And if we do the whole of Through the Looking Glass with 28 figures, 90 pages, it takes a little bit longer than the Age of the Universe so far. So but this is it retaining the order of figures? Yes, that's retaining the order, but otherwise you can put the figures on any page. And the one up here is if you allow more than one figure. So if you have 3 figures on the first page, no figure on the second, then it gets even bigger. But this is good enough to see that we are actually in a bit of a fix here. So, let me do it better. And I claim in some cases we can, in many cases we can't, and this is what the talk is all about. So,
these 11,000 possibilities, they are independent, so you can run them in parallel in the cloud, isn't it?
Yes, but then this one on the bottom is going to have a problem. And the solution wouldn't be solved. You still have to make the decision which is the best. Anyway, yeah. So this is the problem that I want to talk about. We have already a number of text lines between we can make page breaks. These are these T's, T1 to Tn. So we have n such text lines, and we have a number of figures that we want to mix with the two. And in real typesetting that we know about, we typically have more than one set of floating objects. We have figures, we have tables, sometimes we have programs. They are often independent, but I ignore that for now. I just talk about a single second stream, which is the flow stream.
And the stream is lines. The text blocks are lines, basically.
Yes, lines or couple of lines if they are not breakable. Basically, it's unbreakable, a sequence of unbreakable blocks, and between the blocks you can break. And as the target output, the layout, we have a set of spreads, in other words, double pages, typically, possibly with several columns. And we have potentially different sizes of the columns, so the height can be different on such a spread. And we have some kind of rules where we can place the figures, and we have some process description how to put them. So for example, a figure the first figure would go in the top left, and a second could go in the bottom or in the right bottom. Those kind of things could be described as part of this model. So this is sort of our input and the target that we want to reach. And our problem is now to find a way to take this text stream and the figure stream, and map this onto the individual spreads. So the first 50 lines of text go on the first spread, and one figure goes on the first spread, then 51 to 80 goes on the second spread, and figure 2 and 3 go on the second spread, and so on. This mathematical description basically means we keep the order of our text stream, and we keep the order of our float stream, but between the two there is no connection. So it's allowed that the figure floats within the text. This is basically what we know how our typesetting systems typically behave. And this is what we call a pagination. It's a split up of these two streams into pages or into spreads. And the set of all those paginations is what I call this calligraphic P. Now, if we want to find an optimal solution of these kind of problems, we have to define what we mean by optimal. And we do this by deciding on a cost function or an objective function, what it is called. And this is basically a function that takes elements from this and produces some real number, or it could produce some positive integer, if you like. And what we try to find is one pagination that is minimal under this function. In other words, there is no other pagination that has a lower result. And it says less than equal for a good reason. We are not claiming that there's only one such minimal solution. We are just saying we are trying to find one that is minimal. That could be said, if we find one and it is actually minimal, then we say, hooray, we have a solution. So that's the optimization task. The question is, what is this function looking like, and can this problem actually be solved in a suitable fast or slow time? So, how can we do it? I give you 3 examples. The first is the gut decision, as I call it. We just look at each and every one. We don't make assumptions about that there is a structure between in our function. So we really look at each and every one and try to decide what is the best solution. And this is not possible for a very simple reason. It takes too much time. If we just need a second for one decision, this is a good solution, it's a bad solution, or better than the ones that I've seen, then we are already talking about hours for very short documents, and we're talking about, well, the age of the universe for something like a simple one. So you could try to put some structure on the whole thing. And the typical one that people think of is pictures and text have some relation. And the relation is usually you have some reference reference in the text that says, explains something about the picture or points you to it. Some reference, some call-out. And obviously, a possible measure for quality is to say how well is the figure, the picture, related to this position in the text. Because if I can immediately see the picture, it doesn't interrupt my reading. I have the ability to relate the text that tells me something about the picture to the actual picture. If I have to turn pages to find the picture, that interrupts my reading process. So you could think of a measure that says something is of good quality if the picture is nearby that point. And the further you go away, the less good that is. Now, here we have an interesting result from the 80s. If we do this kind of solutioning and say a solution is better if the picture is nearby, then if we write up a formula which is linear, so for example we just count the number of page turns, then this is solvable in a reasonable amount of time. The time grows if the book or whatever gets bigger, but it goes quadratic, so it is not so bad. If we make a small change and we say we do not count the turns, we use a quadratic formula. So for example, if the figure and the picture and the call-out is on the same page, it has a cost of 0. If we have to turn, it has a cost of 1 to the square, which is 1. If we have to turn twice, it has a cost of 4, because it's 2 squared, and so on. If we do this kind of measure, which seems reasonable, saying the further you go out, this is really getting worse, therefore we want to put extra cost onto it. But if we do this, the whole problem gets unsolvable. It gets NP-complete, which essentially means it takes enormous amount of time. Or at least nobody has ever found an algorithm to do it sensibly. Let's say it this way. And a third example, which is kind of strange, but nevertheless it gives you an idea that we have to be careful about what kind of function we can choose. If we say a pagination is good if the call-out is on the same kind of page as the figure. So for example, if the call-out is on the right-hand page, then the figure has also be on the right-hand page. Then we say it's 0 costs. But if one is on the left-hand page and the other one is on the right-hand page, then we say it has a cost of 1. And we sum this up. If we do this, the problem becomes unsolvable. Now, we wouldn't probably think of that as being a sensible way to call something a good quality, but it shows that not every formula at all is possible. And which of those work? Only this one in the middle, and it used dynamic programming, which is, well, the solution in some sense for that space. So we should look a little bit further on what this type of approach can solve for us. Yes?
Question to your third example. If you reformulate your problem, you're doing it on a spread, on a double long page, that's double the size of the page. And then the problem is the call out and the picture on the same page?
No. It means any odd or even page. So I say it's fine if my call-out is on page 1, then everything is okay if the corresponding figure is on page 3, 5, 7, 9, or 11.
Okay.
Yeah. Otherwise, yes, it would be.
Yeah, that's okay. Got it.
So that's a, and if you think about it, these two are so problematic because they communicate over long distance. That's really the issue. The quadratic formula gets bigger and bigger the further you go away. Therefore, you always have to remember where you started. You can't ignore the fact that the callout was on page 2 or 3. It makes a difference later on. And that's the reason why those go bad, basically. Okay, when can we apply programming, dynamic programming? It needs 2 requirements. One is we need to have a problem that consists of overlapping subproblems. And the second one is this strange optimality principle, or as some textbooks says, it exhibits optimal substructure. So what does this all mean? For typesetting, we clearly have the situation that we have the subproblems being overlapping. Why is this the case? Basically, now I go again a little bit in mathematics. This notation here has the following meaning. It means we are looking for partitions from spreads from one spread to a second spread, from spread I to spread J, and we put in all the blocks from position A to TB, and all the figures from C to D. And then we try to find all the partitionings that we can do in this way. So, example, this one here says the partitioning from spread 1 to spread 4 with the text blocks from 1 to 150 and the figures from 1 to figure 4. And you can split this up in, for example, the partitions from the first 2 spreads, text blocks 1 to 80 and the first 2 figures, and then 81 to 150 and the second figures on the other 2 spreads. Now this is one possible split. The next possible set of splits would be up to 110, and from 111 to 150, this is also part of this block. And then, as another example, this one here could be divided up into one that is, the first 2 spreads have the text blocks up to 80, and the first figures, and the second one has 81 to 110, and no figures. And if you see, this one again is the same group as this one. So all these problems overlaps. In other words, once we have looked at the first 2 pages and have put something into it, there are many possibilities how to do the other pages without changing anything on the first 2. And this means that if we look at the whole pagination, we have a lot of those problems that have common subproblems. So this is the case in typesetting and in pagination. We have these overlapping subproblems. Now, optimality principle is a bit more complicated. That's the definition. It has 2 parts. One is saying, if I have an optimal solution for the whole problem, it is also an optimal solution for all of its